Hello everyone, welcome to today's class. And today we'll start to talk about supervised learning models for regression. And we will use about 2 lectures to talk about this topic. And we'll start with the simplest case, linear regression. And then we will talk about how to use machine learning models to do regression. For example, decision tree, random forest, and k-nearest neighbors. And then in the second lecture tomorrow, we'll talk about more advanced regression models such as splines and local weighted regression, etc. Okay. All right. So we are here, supervised learning, and the response variable is numeric, so it's a regression problem. So start from very beginning. So in this lecture, we'll use this data set, Rail Trail. This data set is built in this package, Mosaic Data. You can install and load this package by yourself if you want to code with me. So let's take a look at this data set. The Pioneer Valley Planning Commission collected data north of Chestnut Street in Florence, Massachusetts, for a 90-day period. And this organization, PVPC, wants to understand the relationship between daily ridership and some feature variables. So the response variable is daily ridership, the number of riders and walkers who use the bike path on any given day, right? And totally it's in a 90-day period, so only 90 observations. It's a very small data set. The response variable is called volume, actually. So this is the response variable, the number of people who use the bike path. And then we have a bunch of feature variables about temperature, rainfall, cloud cover, etc. So let's take a look at the data set. So we have a few variables about temperature, high temperature, low temperature, average temperature. And then a few dummy variables about the season, like spring, summer, or fall. Only 3 seasons. And then cloud cover, rainfall, precipitation, and this is response. And then 2 variables about the day of the week. So this one is a weekday. It's a logical variable. Has logical values, true or false. And then we also have another variable called day type. It has only 2 levels, weekday or weekend. Apparently, these 2 variables have similar information, exactly the same information, but they have different data types. So this data set is intentionally designed or collected for regression purpose, and some variables are apparently redundant, and they were included for model selection examples. Okay, all right. So let's start from the beginning. I know most of you, almost all of you have had step 1000 or 200. You have some basic knowledge about regression. But we will start from the very beginning because it is the kind of the foundation of everything. So we'll start with simple linear regression. So a model is called a simple linear regression because there is only one feature variable, one predictor in the model. So basically the model is somehow like this, only one predictor. Right? And the relationship between y and x is linear. And it seems that temperature, high temperature is might be related to ridership, the volume response variable. So let's fit the first model using high temperature only. So let's first create a scatter plot to examine the relationship. Before we fit any regression model, we need to visualize the data. So create a scatter plot. So it seems that there is a moderately strong linear positive relationship between high temperature and volume. Okay. And at least we don't observe very obvious nonlinear relationship. And so we can fit a linear regression model. So the model in, in our example looks like this. A volume equals beta 0 plus beta 1 high temperature plus some random error. And beta 0 and beta 1 are called the parameters of the model. Although they are unknown, they are assumed to be constants. Right? They are fixed numbers. And this is not just one model, rather it is a family of models because different combinations of beta 0 and beta 1 indicate different members in the family. So this is a linear model family. And the error term stands for some unexplained error associated with the ice case. It might be due to different reasons, for example, measurement error or some other issues. So usually we assume that the error term has mean 0 and the constant variance. So which means the mean of the error term is assumed to be equal to 0. And the variance of the error term is equal to some unknown constant, sigma square. So this is called the constant variance assumption. We always assume this for any regression model usually. Although the sigma square is unknown, but it is assumed to be a constant, which means the the value of sigma square should not change with the value of x. It should not be affected by the value of x. All right, so this is a simple linear regression model, and it has a good interpretation. For example, if high temperature, the x variable is increased by 1 unit, then the volume is changed by beta 1 unit on average. Okay. So if it is increased by 1, then volume will be changed by beta 1. Okay, beta 1 can be positive or negative. And also, if the high temperature, for example, is equal to 60, then the value of the y variable volume is centered at this value, beta 0 plus beta 1 times 60. So this is a predicted mean response for y. All right. So fitting a regression model amounts to finding estimates of beta 0 and beta 1, right? Because they are constants, but they are unknown. So modeling means trying to figure out these two, the estimators of these two parameters, okay? And basically from the scatter plot, if you draw a straight line, right, to represent a relationship, it looks like it makes sense. However, the problem is that there are too many possibilities, right? So for example, I just randomly draw 3 regression lines. They all look reasonable, right? But there must be some regression line that is the best, sort of the best model, right? And in this example, in this chunk of code, I actually used a new function called transmute. So transmute is similar to mutate, the mutate function in dplyr, which can add new variables to an existing data set. For example, I take the rail trail and call the transmute function and create 2 variables. X is equal to high temperature, Y is equal to volume. So basically, I rename these 2 variables, but instead of using the rename function, I use the transmute function. So I create 2 variables, X and Y. So the difference between transmute and mutate is it will add new variables and at the same time drop existing variables. So it will remove high temperature and volume from real trail. So I save the result in RT-sim. And then in this data set, we only have X and Y variables now. All right. Now since there are, so this plot or this simulation shows you there are infinitely many possible linear regression models or lines that can be used to represent the relationship. Of course, some of them are really counterintuitive. Even the slopes are wrong. As you see, some lines have wrong slopes, negative relationship. But theoretically, they are all possible models. There are infinite many of them. Then before we see how to find the optimal model, let's compare two extreme cases, the worst model and the best model. The worst model is called a null model, right? Which means we assume that there is no linear relationship between x and y. Right? So no linear relationship between volume and high temperature. In this case, the model will be somehow like this. Oh. Somehow y is a constant, right? The slope, this term is gone, right? It's gone. So it's called the null model because we assume there's no relationship. In this case, the model is a horizontal line, right? Which is actually like this. Y hat is equal to y bar. So this is a mean value of y, a mean value of the y values, right? So this is the best estimate for to predict y for any new observation, right? Because we can only rely on y, and the mean is the best estimate. So this horizontal line is y equals y bar. Okay, so this is a null model. And the second model is the best model in a sense. It's called the least square. It's a simple linear regression model using the least square method. And in a sense that it will minimize the sum of squared vertical deviations, right, of observations from the model. These two models. Let's fit these two models and evaluate these models, compare the performance of these two models. Right? So in R, we use the LM function to fit regression models. In our case, the formula is just y to the x and specify the data set and save the result in mod. Right? And then we will pull out the residuals, okay? Using the RESID function, we can pull out the residuals. Residuals is yi minus yi hat. So this is actually a vector of residuals. Yeah. We call it error dot SLR. So this is the error vector, residual vector for the best model, simple linear regression model. Okay. So how about the null model? Remember, for the null model, for any observation, the predicted value for y should be equal to y bar. So that's why, so the residual will be the y vector minus the mean of y. And save the result in error dot null. So we have two columns of errors. And then we can calculate sum of square errors. Sum of square errors is this. So this is just a review. So we can compare their results. So apparently the null model has a much bigger sum of square error. It has 7 figures. SSE for the simple linear regression only has 6 figures. So the null model is apparently worse. The SSE measures the sum of squared of these vertical distances. So for example, for this observation, the vertical distance is this, is the EI. Squared. Okay. All right, we compare the two extreme cases. Now let's see how to find the best fit model. It turns out that this method, the least square method, can be used to find the best model for simple linear regression. And so it is actually an optimization problem. Namely, we want to find beta 0 hat and beta 1 hat, the intercept and slope, so that the sum of square error is minimized. Right? So namely, if you plug in these two estimates into the regression formula, into the sum of square error formula, you should achieve the minimum. This one must be the smallest among all the possible SSEs for different models. Okay, so this is the least square method. And there is a unique solution for beta 0 hat and beta 1 hat. Right? And the least square estimate that you learned from elementary statistics classes are exactly this, right? These two. Meaning beta 0 and beta 1 hat that can minimize sum of square residuals. And in R, LM computes beta 0 hat, beta 1 hat for you. For example, if we feed the model and use the coefficient function to apply it on the model object, we can get the intercept and slope. Beta 0 hat, beta 1. Okay. So this is the simple linear regression model. All right. Then let's move on. So more sophisticated models actually are very similar to simple linear regression in theory, right? Because they are always trying to optimize a goodness of fit measure over a family of models. For example, we have learned some machine learning models so far. For each machine learning model family, we try to optimize some goodness of fit measure. For classification models, we try to maximize the accuracy or minimize the misclassification error for the test set. For regression models, we try to minimize mean square error on the test set or maximize R-square or some other metrics, right? So anyway, all of these are called goodness of fit measures, right? The different models may use different goodness fit measure, but it's always an optimization problem. All right. Now, how to quantify uncertainty in regression? The problem is that why do we need to quantify the uncertainty? It is basically because we usually only have access to a sample of the population. We usually have access to the data, which is a random sample from the population. Consequently, the model we built using the sample data is also random. So that's why we usually use a hat to denote a model, right? Which is you can, for example, for linear regression, somehow like this. Right? Both beta 0 hat and beta 1 hat are functions or expressions of our data, x and y. Consequently, because x and y are random, beta 0 hat and beta 1 hat are also random. Consequently, the whole model is random. And because it is random, then if we use the model to do prediction or even for these terms like the slope, it is a random quantity. It has uncertainty involved. So how to quantify this uncertainty? We can do hypothesis test. We can also construct confidence intervals for these terms. Right? So in our class, this is not our focus because usually our focus is on prediction, but still we need to know the very basic stuff about it, like how to quantify the uncertainty. Okay. So there are two cases in order to quantify the uncertainty of a regression model. The first case is we assume we know the population, right? Or we actually know the population. We have access to the whole population. Right? For example, in the flights data set, we actually have access to the whole population. Or we can assume we know the population. This is one case. The second case is we don't assume we know the population, or we don't want to make any assumption about the population, right? So for these two scenarios, we use different method. Right? So first, take a look at the first case. We know the population, or in other words, we make an assumption that we know certain things about the population. For example, in a simple linear regression model, if we assume that the error term follows a normal distribution, then we can do a bunch of inferential analysis. For example, we can do a hypothesis test for the slopes, the intercept. We can construct confidence intervals for the mean response, or mean response, or a single response value, etc. Right? So all of these are based on this assumption. The error term follows a normal distribution. And so let's just briefly take a look at this. I believe many of you have learned this in very well in Stat 1221 or other classes already. And so we just take a look. So for example, we can do a utility test about a model, namely want to test if there is indeed a linear relationship between X and Y. So that test will be about the slope, okay? So take a look at the summary result, the coefficient table. The second row is about the slope. Okay? So this row lists all the information about a t-test. So the hypotheses are the null is beta 1 is equal to 0. The alternative is beta 1 is not equal to 0. So if the null hypothesis is true, the slope is equal to 0, then there is no relationship between X and Y. So that's why it's also called a utility test. And for this is simple linear regression model. And everything is listed here. So this is beta 1 hat, the estimate, point estimate. This is the standard error of beta 1 hat. This is a t-test statistic for the t-test, and this is the p-value of the t-test. And from this result, you see that the p-value is very small, 1.7 times 10 to the negative 9. It's significantly smaller than 0.05. And by the way, this 3 asterisk, so this is a kind of indicator of significance of a term. So 3 asterisk means the p-value is greater than 0 and smaller than 0.01. So see significance code here. Right? Indeed, this is smaller than 0.001, but greater than 0. Right? So it's very significant. So this is a t-test. Right? And we can also calculate a 95% confidence interval for the slope. For example, we can just use this simple formula, beta 1 hat plus or minus 2 times standard error of beta 1 hat. And beta 1 hat is given, and standard error of beta 1 hat is also given in the table. So you just need to do a very simple calculation to get a approximate 95% confidence interval for the slope. Alternatively, we can call this function conf_int function to calculate a 95% confidence interval for any term. If you want to calculate an interval for the slope, list the term that is high temperature. Otherwise, you use intercept. All right, so this is inference about the slope. Similarly, we can quantify the uncertainty in prediction of y, but we won't focus on that. So I will just show you a 95% confidence band for the mean response that is created by ggplot. Okay, so if you create a scatter plot and then call the gym smooth function, and at the same time let method be lm, then it will fit a linear regression for your data. And if SE equals true, it will create a 95% confidence interval for the mean response, right, for you. All right. And then let's quickly move on to the second case. The case that we do not want to make assumption about the population. So we don't want to assume that the error term follows a normal distribution, etc. In this case, we actually can use bootstrap to quantify the uncertainty. We have studied bootstrap earlier. Bootstrap is a completely non-parametric method, which assumes almost nothing. So the whole strategy relies on resampling with replacement by creating bootstrap samples. Similarly here, we can follow the same strategy. We can create many bootstrap samples using our data set and feed a linear regression model using each bootstrap sample. Consequently, we will have a pair of beta 0 hat and beta 1 hat for each bootstrap sample. If we repeat it many times, then we'll have a collection of beta 0 hats and beta 1 hats. Namely, we will have a bootstrap sample for the slope and the intercept. And we can easily do inference using this bootstrap sample distribution, bootstrap distribution. So let's see how to do it using R. We need to load 3 packages, the Bloom package, the model R package, and the PURR. The model R package is included in tidyverse, and these two, PUR is also included in tidyverse, but they might not be loaded automatically. So let's see how to do it. First, we generate 100 bootstrap samples from our data set. So sampling with replacement with the same size, and save the result in boot. So this boot is a list of data sets. Each component is a bootstrap sample. And then we call the map function. So this map function is in the PURR package. So this function allows us to apply the same model on different data sets. So for example, we call extract the strap from boot. So each strap is a bootstrap sample. Okay. And then specify the formula, the function. Don't forget the tilde. Tilde LM volume, tilde high temperature. So this is the regression formula. And then data equals period. So that means I will use objects contained in the first argument. Okay, basically it will fit a linear regression model using each bootstrap sample. All right, and save the result in models. So these models contains beta 0 hat and beta 1 hat for 100 different samples, different models. Okay. And finally, we will use this mapdf function to organize the result. You see, we call the tidy function in the Bloom package. Basically, I want to create something like a table. So take a look at the result. 2 rows. Each model occupies 2 rows. The first row is the intercept. The second row is the slope. You see, ID is the model index. Okay, the first model, intercept and slope. So the estimates are actually those beta 0 and beta 1 hats. And also it does a t-test for each term. But these are not a focus usually. We focus on these estimates because our focus is to, we want to build a bootstrap sample for the intercept. And then let's construct 95% constant for the slope using this bootstrap sample of slopes. Okay, remember we have 100 models. Consequently, we have 100 beta 1 hats. There are two ways to construct the 95% interval. One way is to use a sort of more data-driven method. Okay, we use the 2.5 percentile and 97.5 percentile of the bootstrap sample for slope. Okay. And consequently, sort of 95% of the slopes fall between these two numbers. Right? So that is exactly what we want. It's a 95% compatible. Oh, let me draw a picture. Suppose, so this is a distribution of beta 1 hat, right? Some bootstrap distribution of beta 1 hat. And we choose the 2.5 percentile and 0.75, 97.5 percentile as a lower limit. So this is a lower limit, this is the upper limit. And we know that 95% of beta 1 hats fall between these two numbers. Okay. So this can be used to estimate a 95% interval. Right? And we can just use the quantile function to calculate these two quantiles. This is one way. And this interval is not symmetric about the mean of beta 1 hat. We have 100 beta 1 hats. So this one is not necessarily symmetric about this because we only use two quantiles. If you want to assume symmetry, you can use the traditional way. We calculate the mean and the standard deviation of beta 1 hat, and then use the formula mean plus or minus 2 times standard error of beta 1 hat. Okay. So then if we do this, the interval is symmetric about beta 1 hat, the mean of beta 1 hat. Okay. All right, so this is how we use bootstrap to quantify uncertainty for a regression model. You can see that this method is very useful and it can be used on any regression models. No matter how complicated the model is, you can always create a bootstrap sample, create a bunch of bootstrap samples, and then fit the same model on each bootstrap sample, and then create a bootstrap sample for the slope or any parameter actually, and then quantify the uncertainty. All right, that is simple linear regression model and how to quantify uncertainty. Then let's move on to the next small topic, that is categorical experimental variables. So how to understand a regression model with categorical X variables. So consider a variable called weekday. Weekday is a logical variable which has two values, false or true. 28 false, 62 true. Of course, there are more weekdays than weekend days, right? And then let's first examine or visualize the relationship. We want to know if volume and weekday are related or not. So we can create a side-by-side box plot and see if the distribution of volume is the same for the two groups. Apparently, they are not the same in terms of spread or median. They are not the same. And we can also calculate some summary statistics for volume for each group. So apparently, you see on average, the volume on weekends is higher by 431. On weekdays is lower, 350, right? Which makes sense, right? People have more time during weekend, so they are more likely to use the bike pass. Okay. All right, now let's fit a simple linear regression model with only one categorical variable, right? Weekday. And then the model looks exactly like the same, right? Y to the X. I specify the data set. I call it mod2. And then call the summary function to show the fitting result, a comprehensive fitting result. Let's focus on the coefficient table. Intercept and slope. Notice that the variable original was called weekday, but in the regression model it's called weekday true. Right? That is because R automatically create dummy variables for any non-numerical variables. For example, this is a logical variable. You can also consider it as a categorical variable with only two levels. Okay, and by default, it will choose alphabetically lowest value of the categorical predictor as the reference group and create indicators for the other levels. So weekday has two levels. So false or true. And alphabetically, false is before true. Right? So weekday false is the baseline. And it creates a, let me see. Oh, alphabetical lowest is false is ahead of true. So true is the baseline. Sorry, true is the baseline. Right? I need to create a dummy variable for false. Right? It really depends on how you define lowest. Okay, lowest is the latest value alphabetically. For example, Z is the lowest. Okay, for letters. Okay. All right. So it actually created a dummy variable for weekday for the true level of weekday. So that is why it's called weekday true. Right? It combines the value and the variable name together. Right? And then how to understand the slope for this categorical variable? Let me write it in this way. Right? So y is equal to beta 0 plus beta 1x, where x has only two values. Consider one case if x is equal to 0, then y is equal to beta 0. Oh, sorry, not x is equal to, yeah. If x is equal to 1, then y is equal to beta 0 plus beta 1. Okay? So what is beta 1? Beta 1 is actually the difference between is actually an additional intercept term. Okay, it marks the difference between the two levels, the mean of the two levels. Okay? The mean value of y of the two levels. Okay? So yeah, that's it. So let's take a look at the second slide. Okay. So take a look at the coefficients. So 430. So this is the baseline mean. This is the average volume when weekday true is equal to 0, which means is the weekend volume, average weekend volume. Okay. And the intercept is negative 80, which means if weekday true is equal to 1, which means it's a weekday, then you need to subtract 80 from 430. Right? So then the result is somehow like 350. So that is the mean volume on weekdays. Okay? So both of them are actually means. So this is weekday, this is weekend. And the difference is the slope for weekday true. Okay. So this is a simple linear regression model with one categorical variable. All right. Now let's move on to multiple regression models. Okay. So a multiple regression model is just a linear regression model with multiple x variables. Right? So it's very similar to a simple linear regression model, except that the estimated coefficients are now interpreted as conditional on other variables. So pay attention to this. So each beta j reflects the predicted change in y associated with a unit increase in xj, conditional upon the rest of the expanded variables. So holding everything else the same as a constant. So don't change x2, other x variables, other x values, only change xj. So it's kind of like a marginal effect of xj on y. So that is the interpretation. That is the interpretation of beta j. Okay. All right. Then let's move on. So we fit the simplest multiple linear regression model with high temperature and weekday, right? Both of them. And weekday is a categorical variable. Then let's see the result. We have a row for high temperature, so this is the slope for high temperature, and also we have the slope for weekday too, still. And this model is called a parallel slopes model, right? Because if you plot the model, it looks like this. Right? Instead of having only one line, it will we actually have two parallel lines, regression lines. So let's try to understand it, why it looks like this. I will just show you a very simple derivation. And right here, yeah. So suppose you have two variables and x2 is binary. It has only two possible values, 0 or 1. Now consider the zero case. If x2 is equal to 0, then y will be equal to beta 0 plus beta 1 x1. Okay, the last term is gone. And then consider the other case, x2 is equal to 1. Then y is equal to beta 0 plus beta 1 x1 plus beta 2. Okay? Beta 2 times 1, theoretically times 1, which is equal to beta 2. And then beta 2 times 1 is equal to beta 2, which is a constant. So we can combine it with beta 0. So see, we have two lines with the same slope. See, it's the same slope, beta 1, and different intercept. The only difference is the intercept. Okay? If x2 is equal to 1, we have one additional term in the intercept. Okay? And this marks the difference between the two parallel lines. Okay? So that's why it's called the parallel slopes model. Okay? All right. What if we add one more variable? Right? For example, add cloud cover. Right? And then, interestingly, weekday 2 is not significant anymore. Right? Previously, it is, both of them are significant. Right? So see the p-value is greater than 0.01, smaller than 0.05. Right? It's still significant. But if we add cloud cover, it's not significant anymore. And what if we throw all of the variables into the model? In order to denote the full model, we use volume tilde period. Right? So this y tilde period is used to denote a full model. Right? And then take a look at the table. You see we have some NA values or missing values for some variables. For example, average temperature. The model cannot estimate the slope of it. And also the dummy variable for the fall season and also the last variable date type, missing values. And also, most of the variables are insignificant. Only high temperature is significant, and precipitation is significant. And cloud cover is marginally significant. The p-value is smaller than 0.1, but greater than 0.05. Okay. So apparently, we have included many useless terms, right? And some terms are even redundant, and the model cannot estimate them. Right? So apparently, the model overfit the data, and to an extent that some terms cannot be estimated even. Oops. All right. For example, the fall dummy variable cannot be estimated because it is perfectly related. There is a perfect linear relationship between fall and spring and summer. For example, if you add these three together, you always get 1. So x1 plus x2 plus x3 is always equal to 1. Okay? So which means one of them is redundant, right? And because whenever we know the other two variables, the third variable can be calculated using this formula 1 minus x1 minus x2. So this means one of them is unnecessary, okay, totally redundant. In this case, the model cannot estimate the slope. It cannot use it at all, okay? The regression matrix will be singular, okay? And also, average temperature is actually the average of high and low temperature. So there is a perfect linear relationship between average temperature and high and low. So that's why we cannot estimate average temperature. Right? So that raise another question: how to choose the best model? Okay? Which model is the best one? We don't want to underfit our data. We don't want to overfit. Okay? How to find the best one? And in regression, traditionally, we can use this automatic model selection algorithm to select the optimal model. Of course, most of these algorithms use some greedy method, right? So it will be satisfied as some local optimum. It will not do an exclusive search for all possible models, because many times it's not feasible to consider all possible models. So instead, it will try to find a shortcut, right? Find the best model that does not require a lot of calculation. Right? So in our lecture, we will just use one function, okay, which is built in this package, math. So this package is available to all users for R Studio. However, you have to load it before you use the function in it. So we first create a full model. We call it mod 6. It's a full model in the sense that it has included all of the variables in the data set, except for those redundant variables. Notice that I removed fall and the other dummy variable for weekday, the other one. So I included everything else. And then I can use the step AIC function to do a model selection. Put the model here and specify the direction. There are at least three possible directions: forward selection, backward selection, and both, a stepwise selection. If you do a forward selection, you will start from a model with no predictor. And at each step, it will choose the best predictor to add to the model. It is best in the sense that it will explain the most variation, the most amount of variation. Okay. And backward, we'll start with a full model, okay, and gradually remove variables. We remove the least useful variables step by step until it cannot remove anything. And both is the most flexible At each step, it will try to add new variables and at the same time remove useless variables. So we will use this and just call it final. And notice that even if I didn't type anything, I didn't print final, but automatically it will show you the fitting process, the searching process. Starting from the very beginning, we specify the full model with all the variables, and it uses a measure called AIC. We'll talk about it a little later, just in a moment. Just this is a goodness of fit measure. We try to minimize it. By adding or removing variables, the goal is to minimize AIC. So this is starting value of AIC. And then at the first step, it will try everything. Because we start with a full model, so you can only remove variables. So it will try to remove summer only, and then you see AIC is reduced to 821.41. Originally is 823.18. And if we remove low temperature, AIC will be this. And it automatically rank the AIC, the new AIC from smallest to largest. So apparently removing summer is the best option because it reduces AIC to the smallest value. And this is the first step. And then you see in the second step, the starting AIC is 821.41, which is corresponding to removing summer. And this is the starting model. And then it will try to remove other variables. For example, at this step, removing low temperature will yield the smallest AIC, etc. And then until the last step. And the starting AIC is 819.31. So doing nothing. So this is the current AIC. If we add spring, AIC will be increased. Minus weekday, AIC also increased. So essentially, doing nothing is the best option. So then the algorithm will be stopped here. So this is the optimal model with 4 variables. Okay. So this is automatic model selection algorithm using both direction because you see for example, at this step, it tries to remove or add. So occasionally you can see adding variables back. And this is our final model. You can also call the ANOVA component of the final model to see a summary of the searching process. First removing summer and then low temperature and the spring. And also the change in AIC. So the model is trying to minimize AIC. What is AIC? AIC is equal to 2 times P minus 2 times natural log of L hat. Okay. In this formula, P is the number of estimated parameters in the current model. For example, at the beginning, how many variables we have? 1, 2, 3, 4, 5, 6, 7. So in the first model, we have P is equal to 7. And then L hat is the maximum value of the likelihood function for the model, the current model. Because at each stage, it will still use, for example, least square method to find the beta 0 hat all the way to the last slope. So, and then it used that to estimate the likelihood of observing X given Y. So L hat also changes from model to model. With different number of variables, it has different likelihood. So likelihood is a good thing, but if you take log of it and add a negative sign in front of it, it becomes a bad thing, right? So we want to minimize negative log likelihood. And at the same time, if we keep adding terms to a model, the likelihood will keep increase. However, the likelihood, the negative likelihood will decrease, will decrease. But at the same time, the P number of terms is increasing, right? So there is a trade-off between these two terms. So this measure or metric reflects the concept of bias variance trade-off. Okay? It will use this term as a penalty term to control the size of your model. Okay? Because if there is no term, you just want to minimize the second term, then you just use the full model. The full model definitely will have the biggest likelihood, consequently smallest negative log likelihood. However, that might not be the best model because probably the bias is small, but the variance is very big, right? Because the model is very complicated. Remember the trade-off. As the model complexity increases, the variance increase, the bias decrease, right? So the biggest model definitely is not the best model. Okay. All right, so AIC is a metric that considers the bias variance trade-off. Okay. And this is a summary of the best model. Right? You see most of the terms in the final model are significant, except for weekday true. The p-value is slightly greater than 0.1. Okay? However, it is kept in the optimal model because removing it will increase the AIC. Okay, that's it. But if you want all of your variables to be significant, you can definitely remove it. And there are also other metrics that can be used to do model selection. An alternative one is BIC, the alternative for AIC, which is defined in this way. The first term is the same, negative 2 times log likelihood. This is the same. But the second term, the coefficient or the multiplier of the penalty term is different. The BIC uses log n. N is the number of observations in your data set. So generally, usually log n is greater than 2. Okay? So you see, as long as n is greater than 7, unless you have a very extremely small data set, the BIC has a harsher penalty term than AIC. Consequently, if you use BIC as a metric in model selection, you will end up with a smaller model, more concise model, usually. Sometimes they give you the same model, but so the model using BIC is smaller or equal to the model uses AIC. So how to use BIC? It's very simple. Still use the step AIC function, okay? Everything else is the same, except for you need to specify an argument called K. K is a multiplier, right? It's this multiplier. Okay? By default, K is equal to 2, which means it will use AIC. But you can also use log number of rows of real trail, which is log n. Then this is a result if we use BIC metric. And you see, indeed, the model is smaller. So you see the weekday true is gone. So this term is gone. And we only have 3 variables left. So indeed, BIC gave us a smaller model. And also, this trace equals 0 will suppress the printout of the searching process. If by default is 1, then you will see the whole thing from the first model to the final model. But if you want to suppress that printout, you can let it be 0.